There we go. All right, we're recording now. If anybody doesn't want their face seen, you're welcome to hide your screen. That's fine. I totally understand. Okay, so I have this picture of scaffolding here to represent the fact that while I'm focused on interpretation, I will be showing you some about math behind things, because I think it's important for you to understand how the math works in order for you to understand how to interpret it correctly. And I will try to do a really good job of flagging for you when we are in scaffolding land, which is like helping you understand how the math works, versus when we're in interpretation land, which is the things that you will need when you're actually writing up the results of something for a paper. So that's the difference. When I'm talking about scaffolding, that's what I mean. So my philosophy in approaching this class is, it's my experience that statistics has this sort of aura of mystery. People are kind of afraid of it. There's a lot of fear around math and numbers and quantitative statistics. And I really love this little GIF that isn't playing on my computer here, where this is the 10th Doctor from the Doctor Who series, and he's smacking his computer going, why won't you work? And that's how I think a lot of people feel when they're trying to interpret the results of their analyses. We don't want you doing that. We're going to coax you through this process so that you never have to hit your computer or throw it out the window. So I see statistical analyses as tools, and my job here is to help you learn how to use them and learn when to use them. So you need a hammer at a different time that you would need a screwdriver, just like you will need a regression at a different time than you will need an ANOVA. So I have structured this class overall from a mastery learning perspective. The idea behind the mastery learning perspective is that I want you to master all of the things that I'm teaching you. I want you all to be successful. I don't believe in gotcha-ing you. I'm not trying to trick you. I'm not trying to make anybody fail. In fact, it will be very, very, very hard for you to fail this class. Don't turn anything in and you will fail this class, but turn stuff in and you'll be fine. So, whoops. My goal is for you all to be able to think about this quantitative data and this quantitative method like a researcher, so that you're able to talk about regression analysis with your advisor, the results of these analyses with your advisor and with each other, but also so that you can talk about it with your friends or your relatives if you ever get to see them again. Okay. So that's a little bit about my philosophy of this course. Like I said, it's a nurturing class. I'm mastery learning approach to this class. I want you all to be successful. And as part of that, philosophy ties into the syllabus. Now, I've given you a syllabus that I have done my best to adapt to this new online learning framework. However, as always, in all of my classes, I treat the syllabus as a living document. Sometimes whatever I'm putting down, y'all are picking up real fast. And in those cases, we move a little bit faster. And sometimes I explain something and nobody gets it and I have to start over again. And so we need to slow down. So I treat the syllabus as a living document for that reason. I want us to be able to go as fast or as slow as we need to. And this year, I think we need to be especially flexible. So you'll see I built in 3 weeks at the end of class with a to be determined, not sure what it's going to be yet. And in part, that's so that we can be a little bit more flexible with how fast we go with this material. Trust me, I have lots more stuff in my pocket. If we go really fast, we've got lots more we can cover. Okay, so this thing about what questions in the syllabus we can answer, we will not do that because I have that discussion section online and I'll just keep monitoring that. Okay. Now, I did send you information about your data set. For the rest of this class, not every assignment, but for many assignments, I have you using your own data sets that you're bringing. And I do that because my philosophy about how statistics works and the reasons why you would need different tools are because different tools are useful for different types of questions that you might have. And it's really different. The things that I study are like children's math achievement, which is really meaningful to me if you talk about the sort of gender gap between kids and their math achievement. That's a really salient and important question to me, but it's not a salient and important question to everyone. And as a graduate student, when I was learning this, the person who was teaching this class was really into personality psychology. And every single example was about personality psychology. And I just couldn't stand it and I didn't understand it and it was not fun. So that part was part of why I changed it to be really relevant. So I want every question that you ask to be relevant to you in some way. So your very first homework assignment, which is already up on Carmen, is describing your data set, is really all it is. There is a 1-paragraph introduction to sort of tell people who you are or what kinds of things you're studying, and then it dives into information about your data set. You will have an opportunity to meet with Susan, who's the TA for this class and who teaches your Tuesday labs, one-on-one to help you get oriented to your data set if you're looking for some assistance. And I recommend that even if you feel very confident about your data set, please, please, please go meet with her anyway. Okay, so that's what homework 1 is. It's pretty easily laid out. It's pretty clearly laid out. And I have an example of what it should look like at the end of that document. So it should be pretty easy to follow along and answer those questions. Okay. So before I get into a little bit heavier of stuff here, is this making sense so far? Can I get a confirmation? I can see many of you. I can't quite see all of you, but I can see lots of you. Oh, look at that. You can do yes. Awesome. That's so cool. Thank you, everyone. I miss hearing your voices and it makes me a little bit sad, but I'm glad I get to see your faces and your names. Okay, so let's talk about quantitative data. Can I get so let's talk about I don't have to do an official poll. If you have a background in quantitative data, can I get a thumbs up or a hand clap? Oh, cool, it like tells me. And if you've done qualitative data, how about you guys? So we've got some of each. Oh yeah, we can do hand clap for one and we'll do thumbs up for the other. Okay, we'll do that for the rest of class. I'll remember that. Okay, so
if you use the participant tab, there's also so if you go and click like participants, you'll see raise hand, yes, no. People can ask to go slower. They can ask for a break. So you could also use that just depending on your preference.
Awesome. Thank you. You said on the participants tab. Okay, excellent. All right, so let's talk a little bit about quantitative data and what they are. So everyone who's here has calculated a mean before in some way. They've calculated maybe a difference between two groups in some way. What I think we're less familiar with is what numbers look like in rows and columns necessarily. Now, quantitative data are any data that are sort of counts. They can be grades, scores, ratings, numbers. It's turning something that you're observing in the world into a number or numerical representation. So here I have some examples of quantitative numbers. I have Ohio State has a 5% positive COVID test rate in the last 24 hours as of 8/27. 38% of Americans approve Donald Trump's job performance. There are 68,000 students enrolled at Ohio State University. And there were 154 regular season episodes of the television show The West Wing. So as you look at these numbers, I want to put you back in breakout rooms for 3 minutes. Okay, 4 minutes to talk about these 4 numbers, to talk about how some of those are more transparent than other numbers. So as you think about these numbers, think about which ones of those are really easy to maybe replicate or really easy to define, and which ones you have questions about in those numbers. Okay, I'm going to try this breakout rooms again. Maybe. Oh, look, I think I can put you right back in your same rooms so you don't have to introduce yourselves. You can just go for it. Okay, ready? Timer on for 4 minutes. Go. I need a timer. Where did everybody go? Welcome back. There it is. Okay, can everyone use the chat? If you can see the chat window, can you use that to type what your class, your group thought was the most transparent, easiest to understand? One of those 4 options that I gave you. Yeah, we have a lot of people saying the last 2 were easy. And I think I definitely agree with you on this one, 154 regular season episodes, because I've defined the construct very clearly here. There are 154 regular seasons episodes that aired of this particular TV show. Now, is anybody here a higher education scholar, studies information about students in higher ed classrooms?
I am.
Yeah,
Me too.
Erin
Yeah.
and Krista?
Yeah.
Awesome. So that number may mean something different to you than it does to other people. Can you talk a little bit about why that number is not so clear?
So to me, the number is not clear because it's not designating exactly what what kind of Ohio State students they're referring to. Is it just undergrads? Is it undergrads and grads? We also have regional campuses. Are you including all of the regional campuses? There's a lot of ways to quantify students enrolled at the university. And so there needs to be a lot more information about what that looks like.
Yeah, I totally agree with you. Much less clear than the other one. So if I had said there are 68,000 undergraduate students on the main campus, then that would be a little bit more clear, but still is a little bit fuzzy. The other thing that I think is fuzzy about this one is exactly who's online, who's offline. Really good question. And then students drop out in the middle of the year. So then do you count all of the students who were there the whole year or only part of the year, or when were they in line? Like when were they signed up? So all of that has a little bit of fuzz around exactly what that number means. The other two are much more difficult to capture, as is sort of highlighted, I think, within our news coverage right now. Everything's a little bit fuzzy. What does it mean to be 5% positive rate? Well, it depends on how many tests you're doing. It depends on how long you use as the denominator. So my point being, some of these numbers are more transparent than other numbers. This is my example of a bad example of quantitative data because it made me laugh a lot. What's the healthiest site on the internet? For every single one of these, you burn 0 calories. Okay, so what are quantitative data? Data don't know where they come from. You know, we had both Krista and Aaron were able to say that 68,000 number is not clear at all. Whereas to someone who doesn't study higher education, they say 68,000, that's clear, I know what that means. So you have to be the interpreter of these data. You have to understand what these data mean. That is your job. Now, I'm going to dive down in this rabbit hole a little bit more because it's really important. So it's easy to think that quantitative data are equal to facts. And maybe you've heard this phrase, just cold hard facts. Just the facts, ma'am. It's just facts. Look at these numbers, right? Facts are not numbers. That exercise I had you do a minute ago illustrates that it's not equivalent. Just because I say 68,000, it doesn't mean 68,000. It depends on who you count. And who you count is a big part of what actually makes up what the numbers mean. So statistics, it's particularly true for that. So sometimes people, you know, the goal of statistics is to take observations and sort of condense them down, and then summarizing them in more and more complex ways. And so then you come out with something that people will call a fact because it's a number, but it's not. It's all just as positional as anything you will ever do in qualitative research. It's just that quantitative researchers pretend like it's not. So one thing that you really need to be aware of, and why I brought this up, is because almost all of social statistics was invented by people who wanted to prove that white people were better than other races. And they used and cherry-picked information in order to ask questions in ways that showed that white people were better than other people. So most of the founders of modern statistics, most of the ones that have all of these statistics named after them, these people were eugenicists, people who believed you could breed bad things out of races of human beings. They sought specifically to determine whether undesirable traits were hereditary. But think about just even the assumption of that, like who decides what is undesirable? It was these very rich white men deciding what was an undesirable trait. So here's an example from one of Reynold Fisher's, someone who you've probably learned the F test, or if not, you will learn the F test here in a couple of weeks. That's the Fisher test. Fisher published this: relatively more Black people are in jail than white people. Therefore, Black people are more violent by their nature than white people. And you can see that, like, yes, thank you for the shakings of heads. I appreciate that. But I think it's really important, and it underlies for me just how important it is you are the interpreter of the data. It is your responsibility to be the person that makes sure you're not asking questions like this, you're not phrasing questions like this, that you understand where the data come from so you can draw appropriate conclusions about the data. Okay, I already said that. So here it is. You have the responsibility to be the interpreter. That's what that is. Okay, so one more example of what our data. If you read this statement here, 75% of respondents to this survey rated Donald Trump's State of the Union address as great or historic. Here are some questions you might ask yourself. Who is a respondent? How many respondents were there? Were there 4 respondents? Were there 2? What were the response options? And so I'll show you what the response options were because I went to his website. Here are the response options for his State of the Union address. He said, was my speech historic, great, or good? And knowing that these were the response options completely changes your understanding of what this 75% means. It fundamentally changes that. And so you can draw a completely different conclusion than you could before. Those are the kinds of things that I really want you to be looking out for as you're thinking about your own data sets, understanding where the numbers come from. What is the mean? What does it represent? That's what that says. Just, you are the steward of your data. This is your responsibility. Okay. Do you feel responsible? Are you ready to take on the power of data interpretation? I'm excited. Okay. So eventually, regression is going to let you do some really complex stuff. We are going to get there, I promise. But first, the way that I like to connect these new concepts for you is to show you how I explain concepts that you are already familiar with, and then I'll show you how they map on to one another. So I'm going to start by talking about correlations, means, standard deviations, and t-tests, which you should all know. So I'm going to talk about those, and then I'm going to increase the complexity a little bit this time, but we're still only going to be able to do the same kinds of things as means and t-tests this week. In 2 weeks, when we come back, then we'll ramp up the complexity. All right, so you're all familiar with a t-test. So a t-test, what it does is it tests the difference between a continuous outcome between 2 groups. Your 2 groups can be experimental, that may have been how you learned it, but they don't have to be. They can be any kind of 2 groups that you can come up with. Freshmen and sophomores, for example. 2 groups is another way of saying dichotomous predictor. Dichotomous means 2 options. Predictor, in this case, is just what you're using to predict the outcome, or an independent variable. So here are some examples of dichotomous predictors. You've got something that could be a qualitative difference. Is the person female or not? You have a correctness scale. Is the item correct or is it not correct? You have, do you own a pet? Yes or no? No, I do not. I do not own pets. I know. But I don't. There will be no pets interrupting. There may be children interrupting. You never know. All right. As far as t-tests go, t-tests are a specific type of an ANOVA, and an ANOVA is a specific type of regression. So we're learning about regression. So it's this big super umbrella, I don't know. It's a bigger category that holds everything else. By learning regression, you're learning how to do these other things also. So when you have a dichotomous predictor or you have a t-test, I'm going to focus a little bit about the kinds of questions you can ask. So here are some example t-test questions. Do 3rd graders and 4th graders score differently on this test? Are people more likely to get in an accident on a Sunday or a Monday? Are you more drowsy in the morning or the afternoon? Does training program 1 work or training program 2 work? In each of these cases, you can see I have a continuous outcome, test scores, or number of accidents, or how drowsy you are, and I have a dichotomous predictor, something with 2 groups that I'm comparing between. So I have a little example that I'm going to walk you through on a t-test way, and then we'll show you in a regression way. I have 2 groups of people, and I trained them in memory, in a memory span task. I sat them down and I said, how many of these numbers can you remember? 3, 2, 7, 8, 2, 4, 1. And people have to go, 3278241. And then we write down how many numbers they remember. So one group had a feedback condition. So that means that if they got a number wrong, I said, no, your number's wrong, try again. And another group did not get that feedback. They just provided the answer and then kept going. And then memory performance was assessed at the end of the training. And then you want to determine whether one training program worked better than the other, if one of them did. So here's the group information. Here are my 2 training groups. This is my no feedback condition, and this is the feedback condition. I have 24 people in the first group and 26 in the second group. I have a mean score on my memory test of 50 in group 0 and a mean score of 56 in group 1. Here are my standard deviations, and that's all we're going to talk about right now. Mean standard deviations. Cool, cool. Awesome. Here's some t-test output. So we're looking at the difference between the means, and we're testing whether the difference between the 2 means is 0. Is it 0 or is it not 0? So here's that t-test. Here are the degrees of freedom that I have. Here's the significance of that test, and then here's their estimate of the mean difference. Remember, it was about 6 points different from the previous slide. Here's where that shows up within this output. So this, along with the significance test, tells me that there is a significant difference between the 2 groups. This number is significantly different from 0. That's what that means. Oh, look at that. Oh, I annotated that for you. Fancy. I forgot I did that. Okay. I brought that up in order to show you how that plays out in a regression. So we have exactly the same thing. The goal of regression is to get one estimated Y value for each person in your data set. And you do that based on the X. With a dichotomous predictor, your estimated value of the outcome Y is dependent on which group that person's in. So in this case, it's either training group 1 or training group 2. And if they're in training group 1, we'll give them one predicted value. And if they're in training group 2, they'll get another predicted value. So it looks like this. Here is the basic regression equation. We have a Y hat. That means predicted Y. And that's equal to a slope variable times the X plus B0, which is the constant. It's the Y score when X equals 0, which is why they call it the B0. Because look, what happens if I plug in a 0 for the predicted X value? My Y hat is going to be equal to my B0. Isn't that cool? Maybe it's not cool yet. It's too early for that to be cool. Hold on, stick with me. It's going to be cool later. So when X equals 1, so my 2 groups here were 0 and 1. So my X value or my predictor is either going to be a 0 or it's going to be a 1. So when I plug it in as a 0, my Y is equal to B0. When I plug this in as a 1, then it's equal to B1 plus B0. And I'll explain to you what those are in just a second. Come on. So here is an output looking box. This is an output of a regression, because regression is going to calculate the B0, which is the intercept or the constant, which is right here, B0. And then you also get B1. B0, the constant, is the mean of the group that you coded as 0. You've also heard this called the Y-intercept before, probably. Y-intercept. So in this case, with the dichotomous variable, it's the same as the mean of the group you coded as 0. And then B1 is the difference between the 2 groups. So this is the training variable. So that's either no, I didn't have training, or yes, I had training. So here it's different, and I'll show you how these numbers line up. One second. In any regression equation, remember these? We have an intercept, the B0. Can you see my cursor? Okay, good. You have an intercept, which is a B0, and you have a slope, which is a B1. B0 and B1. Now the intercept is always equal. It's always the predicted value when whatever your x is 0. Does that make sense? Because if I fill this in right here, if this becomes, my x value becomes 0, then my y hat is equal to B0. And so that's what the B0 is. And the slope here in any regression is equal to the change in the outcome associated with a 1-unit change in your predictor. A 1-unit change in my training program is easy because that's just going from one group to the other group. I'm going from group 0 to group 1. So one condition is going to have a higher mean performance than the other. That's what this training variable means, this coefficient. The sign of this coefficient, which is B1, or sometimes it's called BYX in some of the readings that you have. That's why I have it here. It's dependent on how the variable is coded. So as I'm going up positive by 1 unit, going from 0 to 1, my training variable goes from 0 to 1. My y value goes up by 6 points. So the training condition is associated with a higher mean memory performance than my no training condition. Okay. And then my t values here are a significance, they're used in my significance testing to test whether this number is equal to 0. So I'm reading across a line every time. So this 0 is null. Remember null hypotheses? Yeah, the null hypothesis is the hypothesis that the number is 0. That's what it means. And so every one of these is a null hypothesis that the number here in this B is equal to 0. And so if 50 is different than 0, we would expect to see this to be statistically significant. This p-value would be less than 0.05. And here, if this number is different from 0, then this significance test would yield a larger t and a significance value or a p-value less than 0.05. And so here, because this variable is dichotomous, this t-value is a test of whether the difference between the two groups is 0. In other words, it's just a comparison of the difference between your two groups. You can also calculate the means of each group in this way. I've got the mean of one group here, it's 50. And then if I add together that with this other group, this training group, I get the mean of 56. They're 6 points different. So a little bit more. So if we look at the mean of group 0, no feedback, and the mean of group 1, I just did those for you. Clearly, I was anticipating what I was about to say. The mean of group 0 here is 50, and the mean of group 1 is 56. I just add them together. You can fill in use the regression equation to calculate those. We'll have lots of practice doing that, so don't worry. So I want to compare that with the t-test output that you may be more familiar with, or these numbers from a t-test. First, we have the mean difference, and you see here that it's 6.3. So it's the same in both. My standard error is the same. The t-value is identical, and the significance test is identical. So it's doing the same thing, is my whole point. Regression, again, can get more and more complex, whereas the t-test is a little bit more limited in what it can do, but this is how they line up. Sometimes you might see it presented in articles like this, maybe a bar graph. One looks smaller than the other. Which one remembered more? The feedback did. Okay, so knowing a little bit about that, I'm going to give you your first application question here. So I'm going to take that idea of the feedback example and I'm going to move it to a new scenario. Here's my new scenario. I have given a survey to some parents and I've asked them whether this is their child's first year in preschool. So these are preschool aged kid parents. And so they could answer one of two ways. They could say, no, this is not my child's first year in preschool. Or they could say, yes, this is my child's first year in preschool. So I have some number of kids, what is this? 39% said, yes, it's their first year. 60% said, no, it is not. The other piece of descriptive information you need is how often does your child write letters? Do they sit and pretend to write letters like the ones in their name? They never do it, they sometimes do it, or they do it a lot. And the mean for all of my participants was just a little bit less than sometimes. Okay, so now what I've done is I pose the question is, do students in their first year of pre-K pretend to write their letters or pretend to write their name or write their letters less often than students in their second year? The thought being maybe that kids who have been exposed to preschool, they might have more experience looking at their name being written down. And so maybe that's why. So here is the output. And I want you all to sit for about 3-4 minutes looking at this output and try to answer these 4 questions. Just jot them down on a piece of paper next to you or on a digital piece of paper near you. Okay, and I'm gonna start a timer. I'll just give you 1-minute warnings. So take 4 or 5 minutes and try to answer all of these questions. Okay, I'm actually going to bring us back early because I forgot that what I planned to do was walk through this one and then give you a second one. So, but since we've already done some of this, I will go ahead and ask, can you pop into the chat here and see if you can answer number 1? What was the expected score for students who were in year 1? Feel free to type a question mark if it didn't make sense yet. Okay, this is, we got. Okay, so let me show you where to pull these numbers. Excellent. Whoa. Okay, so the where we pull these numbers from, I got a lot of question marks. I got a couple of yeses, a couple of answers that make sense here. So here's what we've got. The constant in this case is, let me back up a slide. The constant in this case, no, it's not my child's first year at preschool, is coded as 0. And then 1 is, yes, it is my child's first year in preschool. And so when I come here, the mean for students in year 2, that's confusing. What a terrible example. I will answer all these questions for you, and then I'm writing down to take this slide out for next year because yikes. It's just confusing to have year 1 and year 2 be like reverse coded. So acknowledging that this is a very scary example. So that's what you meant with your question. Like what's going on with 0 and 1? All right. So, whoa. Oh my goodness gracious. All right, there we go. So for children who it's their first year in preschool, we would have to, okay, I'm going to start with children who it's their second year in preschool, because that would be when this variable is coded as 0. So when this variable is coded as 0, I need to be able to, I miss having a whiteboard. I know there's a whiteboard feature, but I hate it. I can't use it. And we tried a bunch of things, but it's fine. I'm going to write some things down and then I'm going to show you. So what we have is, we have the constant, which is equal to 0.903. And then we have first year, and that's equal to 0.018. So I want to show you what I have so far. Can you see that? Sort of. Okay, now I know how much space I have to work with. So what I'm going to do is write out the regression equation. So the regression equation in this case is always y, because that's my outcome. The y variable is equal to, oh, wait a second. I know. Hang on a second. We can solve this problem. No. Yes. Ha! That's better. Now that you can see, I assume. Okay. So we're always going to have a y value. And y is equal to, it's always b0 plus b1 times whatever x is. That's always regression. So what we have is y. We don't know what y is yet, but we know what b0 is. b0 is always the constant. So that's 0.903 plus b1, which comes from right here, 0.018 times whatever x is. Okay, when it's the second year in preschool, x is going to be equal to 0. When it's the first year in preschool, x is equal to 1. And so what I can do here is say for any random person that I pick out of this sample, if their X value is 0, then I would plug a 0 in right here, which cancels this whole thing out. And therefore, when it's the second year, their expected score, can't spell, equals 0.903. All right, we're gonna do lots of these. So if this one is not quite sinking in yet, it's okay. That's why we have 2 weeks for you to play with your data. And we're gonna come back and do a lot more of these before I set you loose on trying to do them yourself. Okay, for this one, when X equals 1, the expected score is going to be equal to, I'll plug in a 1 here. So it'll be equal to 0.903 plus 0.018. So my expected score is equal to 0.9, 9 to 11, 28, I think.
It's 2-1.
Oh, God. Thank you. I'm so bad at math. I'm so bad at math. It's terrible. I can't add anything together. All right. So that's where I get those 2 responses. I'm going to back up a slide. I just backed up 17 slides. Okay, so that's how I get the expected score for students who were in year 1 and the expected score for students who were in year 2. The mean difference between students in year 1 and year 2. Oh, I have a message. Thank you. Yes. The mean difference here, that comes straight from this guy right there, 0.018. Yes. Now this question, is that significantly different from 0? We get that from the t-test. And so in this section over here, we would look, and this t value is pretty small, and my significance test here is pretty big, which means that this number is not significantly different from 0. So that means there's no difference in this y for the people in these 2 groups, who it is their first year in preschool and it isn't. Okay. Do we always look at the top line? No, and I didn't look at the top line for significance there. So this right here, we're going to read across the line. This is the significance of the constant. So this is the number 0.903 significantly different from 0? And the answer here is yes, this number is significantly different from 0. This is the t value, which you probably, did you have a stats book and you had to like open it and go to the back and like look in a table? Yeah, that's what that is. So this is just doing that automatic stuff for you. So here, so this right here is the significance of this 0.903, whereas this line right here is all about whether this 0.018 is significantly different from 0. Okay, so I have another example, which is the same idea. This is literally the same question. Hold on. Oh gosh. In this literally the same question here, it just has a different like accuracy this time. Instead of being about frequency, this is now how accurate are the letters they write. But in this case, if you look at the same thing here, this is the question of the constant. And in this question, the constant is, again, second year in preschool. If this is the second year in preschool, then the mean accuracy level was 2.2. But if it was the first year, that accuracy level is 0.27 lower. And the question of whether these numbers are significantly different from 0 is tested here. So is this number 2 different from 0? Yes, it is. And is the group difference different from 0? Yes, it is. That's a statistically significant difference. So kids in the first year of preschool are scoring about 0.27 points lower than their peers who are in their second year of preschool. And I'm not kidding, I actually do have a spot in my whole journal where I write down bad examples and say, take them out. Okay. So briefly now, that is an overview of how to compare two groups, which is something you've always been able to do with a t-test, but now you should be able, well, you don't know how to do it yet, but you know that it can be done using a regression. You will learn how to do it in lab in 2 weeks. And I'll do another one of these dichotomous predictors for you next time, which is, again, in 2 weeks, not in 1. So I know that's a lot to take on. The next thing I want to talk about is correlations. But before I do that, I'm going to give us, let's see, 5:20. I'm just sort of timing here, sorry. Ah! I'm going to sit here for 2 minutes while anybody needs to get up, get a glass of water, whatever you need to do. We're going to try to end right at 6. So take a quick break so we can all de-Zoomify. I'll sit here though if anybody has questions.
Hey, I have a question. Can I speak or do I need to write?
You can speak, that's fine.
Okay, so
Just
if you,
where are you? Oh, there you are.
yeah, hi.
Hi.
So if you go like the slide before, the one you showed, I wanted to clarify if I've understood it right. Okay, so the first, yes. This one, the first one that is constant, we read it straight. And the next line would be diagonally, I read them.
No, it's still straight across.
Okay.
It does look a little strange because this is just a big text box. Let me see if I stretched it out. I didn't. But this line right here, does that make sense? Not really.
Yes,
Oh
the
my
below
gosh.
line.
This is all one piece of information.
Okay.
So this is all talking about the same number. It's just this name happens to be very long, and so it wraps over along here, and it can't edit it. Let me see. I think I have other examples. I mean, I know I have other examples down here somewhere. So like this one, you see how it has training and it's just on one line? Is that a
Yes.
little bit clearer? Is that the confusing aspect of it, is that it's a big block?
Yes, because like there are two things, and then like the first one is the below line, and then the independent sample test is the first line that you have marked. So I was like, okay.
Independent samples. In this one?
Oh no, in the same one. If you go earlier one, it's just the way you highlighted it, so I got confused.
Okay, so
No,
it's not this one,
it's the below one. Yes.
this one. Okay, yes. So each one of these you will read, eventually we'll get to the point that you have lots of them. And
Okay.
every time you're going to read straight across. So this is like the descriptor of what the rest of these numbers are referring to.
Okay, got it.
You don't
Yes.
have to get it. You can keep asking me. I'll keep trying to explain it in different ways.
I got it.
Okay.
Thank you.
Hi, Dr. I got a question about the mean.
Yes.
Is it B like 0.903? Is that it?
Yep.
Okay. Why isn't it 0.018? Or is that for the is your child? Those are two different questions, I think, right?
It is. So the 0.018 is the difference between kids in the first year and the second year of preschool.
Okay.
And so the mean for kids for whom it's the first year of preschool is 0.91. No, 921.
Right.
It's adding them together. Let me back up to this one, which I think was a much clearer example, where in this case, this one right here is the mean for those kids who did not get the training.
Mm-hmm.
This is the difference between the kids who didn't get the training and the kids who did get the training.
Mm-hmm. Right. That makes
So-
sense. Thank you so much.
Yeah. Mean of 1 and mean of 2. Mean difference. Wait, I also really liked this. I actually got the means. Here they are.
Awesome.
Okay, so if this helps right here, here are the actual raw means that I pulled from averaging them.
Right.
So I have 50.167, which is the same. That's how you can see that it matches up, because it's the estimate when the training is equal to 0.
Mm-hmm. Awesome.
And in this
Thank-
case, when training is equal to 1, it's the difference between these two.
Right. Thank you so much.
Yeah. Go back to the slide you inserted and show us the calculation of the first example. Oh, this one? This example? Abby. Where's Abby? I can only see some of you at once. I will also post the updated slides at the end so that you'll have them. And theoretically, we'll also post the video, assuming that all the bits work the way they're supposed to work. I think, go back to the slide you inserted on the spot and show us the calculation to the first example. I think this is the first example. I wanna do this for you. Help me. Well, I'm gonna do it for this example here. So here's our equation, y equals x1 times b1 plus b0. I'm going to do it the other way around because I think it's easier. It's addition, so they can go in any order you want. So I'm going to do them in this order because this is the order that they come out in the output. So y equals b0, which in this case is 50.167 plus b1, which is 6.372 times x, or x1. I call it x1 because later on we can add lots more x's, but right now it's just 1. All right, so if training equals 1, that's the people who got the training. I'll start with training equals 1. Then we have y equals $50.167 plus this, where x1 is equal to 1. So times 1. Oh, what did I do? Okay. Go over there. So that's equal to 56 point something. Oh, it's over here. 53. Okay. If training equals 0, then I have y is equal to, again, I use the same equation, 50.167. But this now becomes what? Anybody know?
0.
0.
0. It's just 50. And that plays out right here. 50.167 and 56.
6.53.
Ding. Ooh, that is working. Okay. 0. Okay, good job. So now let's do, so this is really interesting because when I teach regression, I've taught it both with that dichotomous predictor first, so it's like a t-test, or I've taught it so it's like a correlation first. And I've done it about evenly both ways, and it's equally confusing whichever one I put first. But some people really like one and some people really like the other. So if the first one isn't jiving, see if the correlation does, because it might. So the whole idea behind this is that with a correlation, you can have, there's two ways that two variables can be related to each other. Okay, they can be related perfectly or exactly or not perfectly or not exactly. An exact is a perfect correlation. So that's something like, whoops, something like minutes is always equal to 60 times hours. So 1 hour is equal to 60 minutes. So if I go up by 1 hour, that's equal to 60 minutes. 2 hours is 120 minutes, and so on. There's no error. It's always the same. You know one, you know the other. The predicted values are always going to be the same as the values you observe. But with inexactly, those relationships are less than perfect. And that's really mostly common in everything that we do over here in the College of Education. We never predict anything perfectly, ever. You're still going to get a predicted score, but that prediction is not perfect. And so it looks something like this. Who's seen a scatter plot like this before? Oh, yeah. Awesome. So we have each point here represents 1 point. So for people who study children, this might be students. For people who study universities, this might be 1 university. For people who study principals, this could be 1 principal or 1 district. So each one of these points represents 1 person, place, or thing that you're measuring. And this is one thing you're measuring them on, and this is the other thing you're measuring them on. And you can see that right here, I have my prediction. This is my predicted line, but my points are just falling any old place, regardless, ignoring this line. My predicted values, you calculate the same way that you did before. Remember when we had, like 1 minute ago, when we said 60 minutes equals 1 hour. So we can make a regression equation out of that. Y equals 0 plus 60 times x, where x is minutes. So we can have the same equation here, but if it's not observed, if it's not an exact relationship, then those points can just fall anywhere, helter-skelter.
Dr. Logan.
Yes.
So I just, I'm used to seeing this as y equals mx plus c. It's the same thing, right?
It is exactly the same thing.
Awesome, yeah.
Spoilers, I think it's like right here. I write it like that in a minute. Yes, it's exactly the same thing. Y equals mx plus c or y equals mx plus b, which you probably learned in like 7th or 8th grade for the first time. The slope of a line. Back when you were learning like coordinates, like 2, 3. Yes, it's exactly the same thing. We're just going to start adding subscripts because we can make the equation more and more and more complex. Before, when you were learning the slope of a line, it was usually you have one thing you're using to predict one other thing, which is what we're going to do today. As we keep going, you can add more and more things and make it more and more fun. So let's talk about residuals. Residuals is a fancy word for the word error. And an error is just how far off your guess was from what actually happened. So for example, fancy. Okay, never mind. That's annoying. So for example, this right here, this guy outperformed where I thought he was going to be. He's up here above my prediction line. He will have a positive residual because I thought he would be here, but he was way up here. This guy has an even bigger positive residual because he's way up high, farther away from the line. This person will have a very small residual or a very small error because they're really close to what I thought they were going to be. So they are very close to the line. So their residual is really small. Then this person over here, she's totally underperforming where I expected her to be. I thought she was going to be way up here and she's way down there. Okay, so those are errors. So this basically all that, so you're used to this as a correlation, right? I think you've seen these as sort of scatter plots, correlations with a line between them. What regression is going to do, and I'll tell you about it more in 2 weeks, is that all we're going to do is talk about the extent to which we are able to reduce the amount of error in these predictions. So we're going to start out with just noise, and then slowly as we add more stuff, we're able to see how far away these points are from these lines and see if we can shrink those errors. Less error is good. Okay. So if I can, you can make an equation for this, just like I talked about before. You've got this equation here, y equals 0 plus 2 times x. My 0 is implied, but I'm going to add it, 0 plus 2 times x. And so for every value of x, you can get an expected value of y, just like we did before. Only last time we only had 2 values of x. We had 0 and we had 1. Now we have lots of values of x. So I can keep plugging things in. What if the scale was different? This is just me moving things around. You can get to, instead of it being 0, now my scale went from 95 to 115, and so now my y-intercept is 100. But this look of this relationship is the same. I don't actually, that is less important. I'm not very concerned about you understanding that right now. All right. So, in summary, you have an inexact relation, which allows for error. And then you have the predicted value of any estimate, which is the estimate of the observed value. So I'm estimating where I think people are going to end up. My inexact relationship is taking the form of this equation here, which is just another way to write y equals mx plus b. We have 3 important values to look at here. This is the constant or the intercept. So you're used to it as the y-intercept. I just showed it to you as the constant in those previous equations. And then we have the slope of the line, which is the b1. And we have error. You can also write it without the error term, like this. Y hat equals b0 plus b1 times x. Now the reason why these are different is because it's the difference between the slope, the equation of the line versus the equation of all the points. So the points I have to include the error, but if I'm estimating a y hat, then I'm talking about the line and not about individual points. This is weird. I've never lectured sitting down before. Okay. So all regression and correlation are about estimating and quantifying how inexact that relationship is. Now, the way we determine where the line should be is all based on math, and I'm going to show you a little bit about it in the time we have left, about how we do that. So a correlation, backing up for a second, a correlation is any time we're describing the relation between 2 or more variables. There's no assumption that one variable is influencing the other. It's just that they are sort of happening around the same time. Here are some questions you could examine with correlation. I have, do kids' math skills relate to their reading skills? Is the amount of water consumed in a day related to how happy they feel? Now, regression, we have a predictor and an outcome. So in a regression, instead of just saying these two things go together, you're saying one of them is predicting the other. It could be that they're co-occurring at the same time, but you're picking a directionality. And the reason that that's important is because the dependent variable is thought to influence the independent variable, but we don't actually have any assumptions at all about what's influencing that predictor. Could be nothing or something. So the goal of a regression, again, in the continuous version or the dichotomous version, the goal is to get a predicted score for every single person. And it's influenced, in this case, by this independent variable, or the predictor, the x. So we want, oh, here's that slide. Woo. We want a predicted y for each person. The textbook that I have for you as an option refers to it like this. This is the notation that he uses, Cohen. It's y hat sub j. That just means for a person. Sub j means like for a for someone with a j name. Y hat for j person is equal to the b of the y related to x for the x for that same person plus b0, which is your intercept or your constant. But it can also look like this: x1 and b0, or this one with the error term. It can also have y equals mx plus b. It can also be in the other order, because addition, it doesn't matter. Y equals b0 plus b1 times x1, for example. So we can just flip-flop those around. Okay. So within the regression equation, I'm going to break this down a little bit more. We have the regression of y on x. This is the equation for that line that we saw a minute ago. This represents the rate of change in y per unit of x. And that sounds real fancy, but it's actually real simple. So I'm going to break down what that means. A unit is what one number change represents. It could be points on a test. It could be dollars. It could be years, number of publications you have, whatever x is measured in. This is called a regression weight or a b weight, this b. And then the b0 is called the regression constant or y-intercept, and it represents the point at which the regression coefficient crosses the y-axis. Or, as we learned in the last one, it represents the predicted score on y when x equals 0. Okay. So the b weight, again, we're representing the expected change in y for a 1 unit change in x. What is 1 unit change? So if my x is how many cups of coffee I drink, measured in number of cups of coffee, then 1 unit is 1 cup. If my x is score on a math test in the percentage points, like out of 100, then 1 unit is 1 percentage point. It's the difference between a 97 and a 98, or a 2 and a 3. If my x is the number of West Wing episodes watched, then 1 unit is 1 episode. If I've watched 3 episodes versus 4 episodes, that's 1 unit difference. Which means, why is it called that? Let's look at this. When we look at this regression equation, as this number here, x1, goes up by 1, if I go from, say, 0 cups of coffee to 1 cup of coffee, then I'm going to multiply this by, they're going to multiply these together, and that changes my expected score by however much your b is. Don't worry, I'm going to do that a lot more times. Where did I go? So here is an example, an example data set, so I can walk you through how this looks and how it works. Here I have 15 fake people, and this time variable represents the number of years it's been since they earned a PhD. Here's a person who's 1 year out. Here's a person who's 10 years out, 28 years out. So 1 unit is what in time?
A year.
1 year, correct. Publicat is represents publications. So this person has 2 publications and this person has 21. All right, so that's our fake data that comes straight out of the Cohen textbook. I don't want to calculate these right now. We're going to wait on how to calculate these. So just stick with me. I'm going to remember. We've done enough. That's enough math. Hold on. La la la. Guess what? I promise you're going to calculate a regression by hand, but we're not going to do it today because I want to get you to the interpretation because the first time was a little bit rocky for me in the way I explained it. So now this is, just trust me, this is the regression equation that associates publications with number of years from PhD. So in this case, I'm predicting the number of publications that someone has, and I'm predicting it based on the number of years it's been since they graduated with their PhD. So what I can do is I can plot this line just using your old y equals mx plus b methods of your graphing calculator. Do they still make you buy graphing calculators in high school? Does anybody know? That's absurd. The old TI 83s or something. All right, when I graph it, this is what it looks like. Each one of these points represents a person. So here's that person that had, 10 years since they graduated. Here's that person with 28 years since they graduated. And then on this axis is the number of publications that they have. So there's my line through my scatter plot of points. I don't have them numbered, but here I've got some positive and negative residuals. Here's somebody with a negative residual. They have underperformed. I expected that with 20 years of experience, they'd have at least 10 publications. Do you see how I did that? 20 years comes to about here. That's like 12 publications. That's how I did that. Comes to about 12 publications. But they didn't. They only had about 4. Okay. So those are my residuals. And let's do the slope. So I have a slope and I have an intercept. My y-intercept here is the number of publications that I would expect for someone who just graduated. So someone who has 0 years from PhD, right here. Doo-doo. You see where they are on my line? You can see that that number is about 3.11, right where they hit that y-axis. Okay, that's when my x equals 0. And then for every year out of their PhD program, I expect them to publish about half a paper. Meaning, in 2 years, I would expect them to have published 1 paper. And it doesn't matter where I go on this prediction line. Wherever I go, it's still 0.468. The slope is the same the whole way across. Between year 5 and year 6, they're still publishing half a paper. Year 6 and year 7, still half a paper. Is this easier than the other one? Yeah? Okay, maybe I'll start here.
I have a question.
Yeah.
The only thing that changes when we are doing this is the 3.11. Like as the years go by, it changes, but the constant remains 0.468.
So no, both of these numbers stay the same no matter where you are, because this number always represents what the y value would be when x equals 0. which means, so even if my X here, if I'm plugging in 15, so at 15 years, oh God, 0.468 times 15 is a number that's probably close to 7. So then I would have 7, and then I still add 3.11. So 7 plus 3.11 gives me 10, 11 publications. And we'll see how close we are there. 10 publications. See how it lies right on that line, that 10 line?
Yes.
So that is how I get the expected score for each person along that line. So this number will change. All of these numbers will change in any new relationship that you're investigating between any two characteristics or any two things.
Got it.
But no matter where I move here, this number is the same. All right, so if my years from PhD is 0, that means somebody who just graduated. I expect that they have 3 publications. And if they're 30 years out, I can plug that in. 15-ish plus 3 would give me, wait, I'm sorry, I did that too fast. I'm going to plug 30 into this X value. So 30 times about 0.5, because I'm really bad at that, gives me 15. So then 15 plus 3 is 18. And so for my 30 to get me to 18, you can see that it's pretty close to 18. Okay. Now I did this again just to say that in order to get to 1 publication, you needed 2 years. 2 years to get to 1 publication. Otherwise, you're at half a publication per year. So that's how the equation of the slope of this line works. And so the last thing I want you to do is to do a quiz in Carmen. Oh, this is tough. Do a quiz in Carmen here that will walk you through. I have one example of a dichotomous predictor and one example of a continuous predictor. And I want you to try and interpret the results of those things. Here is the setup of how that works. I have a panel of judges that have rated the taste of popular cereals. My data set also includes some nutritional information like number of calories, number of grams of sugar, number of grams of fat. And then you have 2 hypotheses. You have a friend here that you're working with who thinks that flake type cereals, which are the type 0 cereals, that those types taste way better than cluster type cereals, which is type 1. And then you have another friend who thinks that higher sugar content is going to obviously result in a more tasty cereal. And so that's the setup for these 2 regression equations. And what I would like to do, if you all can stay on, I would like to give you 10 minutes to do this quiz, and then I'd like to have 5 minutes after that to go over the results with you. So that'll put us at 6:05, which is a little later than I had expected. If you're okay to stay that late, that would be great. Otherwise, I'll record it and we'll put it up later. Let me see. Is that quiz open yet? I think I set it to open at 6.
It's not open yet.
Okay. Let me add it. Okay, hopefully you should now be able to see that. And actually what I'd like to do is have you all do the same thing in your breakout rooms. Can you work together on these quizzes and chat with each other to help each other? So I'm going to put you back in your breakout rooms. I'm going to do that for about 8 more minutes. So you have the rest of that time to work together. And I'm going to do that now. See you in a minute. Oh, man, this is a lot harder than I thought it was going to be to transfer. Oh. Uh-oh. Well, where were you, Krista? What happened? Well, hi, Abby and Krista. You all want to work out here? I can wait. I can't hear you. I
I
can.
was about to say, I don't know. I don't believe I know what I'm doing, but you know, so anywhere.
What do you remember who you were with last time? I can put you back in your same group.
I was with Jamie and Russian.
Okay.
I know I was in a group with, I could remember if we had them still here because I could look at the names, but I can't remember because I.
Oh, sure. Well, why don't you two, you want to work right here while I'm here, and I'll just ignore you mostly. And then if you want to ask me something, you can.
Okay.
Sure.
All right, equation 1. What is the outcome? Y hat.
Here, I'm going to even take these out so you guys can talk without worrying that I'm judging you in any sort of way, even though I promise I wouldn't be.
Okay. Equation 1. The outcome Y.
Hi, I'm sorry. My boss screwed up my work schedule, so I am at work trying to multitask. Give me just 1 second.
So I got kicked out of Zoom for a bit, like during the lecture. So I think I might have missed some of this either way. So I don't even really know.
Okay.
I don't believe. Okay. We don't. I don't think. I want to make sure. I had somebody come up the other day. They never even swabbed. No, it's negative. Okay.
Okay. So equation 1 outcome.
No.
So I think for that one, it would be taste.
Okay, that's what I was thinking.
So like
too.
why? Yeah.
But the expected taste for flake cereals, so the constant, so that would be the 59.31, right?
Yes. Yep.
Okay.
For cluster. So a cluster would be a 1 because this is dichotomous. So that would just be 0.31 plus the 1.1 because it was times 1. So that'd be the 60.41. The mean difference. With the mean difference would be, or the expected difference would be the 1.1.
Yeah.
X is the number. Let's see, sugar. There's the slope. Okay. Let's do this intercept.
So the X in 2 is sugar.
Mm-hmm.
Slope value is 2.81. The intercept for equation.
Okay. Awesome. So we're headed all back. It looks like we've got about 10 more seconds until this is all done. So what I'd like us to do is go through all the questions one by one. I see a lot of people scored an 8 on this out of, I think it was out of 8, which means it's making sense, at least at the level that I'm interested in having it make sense for you right now at this stage. I'm gonna just check. Oh gosh, I need like 3 screens. It's very tough to see everything I need at once. I would just like to say for the record that I was not ever one of those people who thought that teaching online was easy. And I am right. It is hard. Okay, I'm looking, it's not showing me how to moderate the quiz anymore. Show me the scores. All right, well, let's just go through them one by one. Back. Question 1. I'm going to try to screen share with you. There we go. Whew. All right. Question 1. We have what is the outcome Y for question 1? And the way you figure that out was by reading the instructions. So here I say the predicting taste, which means taste is the outcome. I'm predicting it from serial type, so serial type is the predictor. Next we have, oh yeah. That makes me so happy. Good job, everybody. I'm proud of you. Look at that. Everybody got this next one right too. Yay, good job. Okay, so we have this one in equation 1. What's the expected difference between flake and cluster cereals? That is this coefficient right here. That represents the difference between my 2 groups. Then next I have the different equation 2. What is the X? We have sugar is the X here. It's right there associated with the X. So that's kind of a giveaway. Okay, and then this one, slope value. And then the intercept value. Nice job. And then this one was the trickiest one here. Expected taste score for cereal when it has 0 grams of sugar, but you all got that one right. So good work on that one. Okay, if you were feeling good about that and how that went, then you are right in line with where I'm expecting you to be right now. And you should be really well prepared for reading the next bits that you need to read and for getting prepared for your next class. So awesome. Does anybody want to, if you have any questions about that, feel free to stick around for a little bit. I'm going to sit here for another couple of minutes and can answer some questions around this. And otherwise, get working on your data set. Email me if you're having trouble with the data set. Please, please, please meet with Susan about your data set. And then I'll see you in 2 weeks. Okay. And I'll post all the readings and everything for next week, tonight or tomorrow.
You.
Yeah, thanks everybody. Nice to meet you all.
Thanks.
Thank you.
Bye.
Thank you.
Bye.
Thank you.
Okay, I'm gonna